Okay, good afternoon, everyone, and welcome to the second ITI CIRI webinar for the month of March. Today's talk will be on the power grid outages in FEMA Region 10, its causes, impacts, and mitigation. The speaker today is Al Valdez, who's Principal Research Scientist at Information Trust Institute. I've heard Al speak about this topic on several occasions, and I'm always very impressed. Not only am I impressed with Al's knowledge and enthusiasm for the topic, which I think you will be as well, but I'm also impressed by the many very interesting facts about the unique threats and hazards that are faced by our friends in the Pacific Northwest. It's really interesting. The FEMA Region 10, which includes Alaska, Idaho, Oregon, and Washington, really has a host of threats, both natural and man-made, that make it a very unique sector, and therefore this project also very unique. Region 10 is diverse and includes the high-tech corridor between Portland and Seattle, as well as resource-based economies east of the Cascade Mountains in Alaska. And the region includes major urban areas as well as rural and tribal regions. It features rugged terrain, major geological threats, both from earthquakes, tsunamis in the coastal regions, volcanoes, and wildfires. And we think we have it bad sometimes. Al's project was initially by a request from the Department of Homeland Security's FEMA Region 10 to provide assistance to them in drafting a threat hazards analysis report on the region. Should it incur a long-term and broad-scale power outage in the region. And some of the unique natural threats of the region make such a disruption a much higher probability than in the rest of the country, although many of the lessons learned from Al's study could definitely be applied to other FEMA regions as well. Power grids are subject to a number of threats and hazards that include natural, accidental, and malicious. Let's talk about cyber, as well as physical sabotage. Catastrophic event leading to a protracted wide-scale outage would have significant impacts on interdependent infrastructures, vulnerable populations, and economic activity. And so this presentation will summarize the study that was done in collaboration with FEMA Region 10 in that regard. By way of background, Al is a principal research scientist with the University of Illinois Information Trust Institute. And he's responsible for a portfolio of diverse research activities, including the Cyber Resilient Energy Delivery Consortium, which was previously the Trustworthy Cyber Infrastructure for the Power Grid Project. Also, the Illinois Center for a Smarter Electric Grid. Al's research interests focus on security and resilience of infrastructure systems, particularly innovative techniques for intrusion detection, as well as security implications of renewable energy integration and smart grid mechanisms. Al is very active in international collaborations with KTH, which is the Swedish Royal Institute of Technology, through the University of Illinois' INSPIRE program, as well as Netherlands' equivalent of the NSF, the NWO, and the European Union, where he is an external advisor to the Success and previously Chrysalis projects, which are about securing critical infrastructure. Al holds an AB degree in mathematics from the University of California, Berkeley, and a Master of Science degree in operations research from Stanford University. With no further ado, let's welcome Al Valdez.
Randy introduced a lot of the points of my talk, so I'm just very briefly going to talk about what the project sought to do. And this is a very complicated project. My specialty is cybersecurity and resiliency, mainly in energy systems. And this was quite an interdisciplinary study, as will become apparent. But one of the things that's important is infrastructure interdependence. We worry about, okay, hacker gets into the grid, lights go out. What do? Well, a lot of things that ripples into a number of other infrastructures and into population impacts and so forth. There are hazards that are unique to the Region 10 grid. There are hazards that are present in the Region 10 grid that are not unique to that region. The study looked at population impacts, and one of the things that we looked at in some depth is the implication of losing high voltage transformers, and that will become more clear later in the talk, as well as some of the things that you can do by way of mitigation and also resilience. So mitigation, technically defined by one of the subject matter experts who participated in the project, are measures you can take beforehand in anticipation of such an event. And resilience is from the Latin to jump back, or to jump again, which is how you bounce back literally from an event of this type. So it's this project was a CIRI partnership with FEMA Region 10, and as Randy said, that is the Pacific Northwest, Alaska, Idaho, Oregon, and Washington. And FEMA puts together these threat and hazard risk profiles for the various regions in FEMA, and they look at various infrastructure sectors. We were tasked to look at the grid, but as we all know, the electric infrastructure is the most important infrastructure that there is. It's the infrastructure in which all the others depend. There was something a few years back that was considered the most important invention or innovation of the 20th century, the electric grid, that is. And so, you know, infrastructure interdependence is a very big factor. As pointed out, there can be natural and human-caused threats. The human-caused can be deliberate acts of physical sabotage. We're increasingly seeing acts of cyber sabotage. And the system is becoming very complex. I'm sure we've been hearing about smart grid now for maybe a decade. And you know, sometimes things get configured incorrectly. Sometimes there are what engineers call corner cases, which is something that's outside of what the system was designed to do, and then the system does something unexpected. We looked at the potential impacts, economic, population, health, and so forth, and as I mentioned, the mitigation aspects. A little bit about infrastructure interdependence. As I mentioned, all critical infrastructure depends on the grid, and there are, in FEMA parlance, there are the four big infrastructures that are in no particular order: communication, water, transportation, and energy. Now, each of these breaks down in different ways. Energy, immediately you think of the power grid, but also in the energy infrastructure you have things like, for example, would you be able to pump gas at a gas station? And you've often seen if a big storm is forecast, one of the things that the news people always show is look at the lines at the gas station, because everyone wants to be sure their tank is full before the storm hits. And as I mentioned, everything depends on the power grid, including, of course, the power grid itself. If you lose a significant fraction of the grid, what is called black start is a major challenge. You have to bring back the grid in pieces according to procedures depending on what is still intact, and you have to do it in such a way that you're balancing load and generation at all times so that you don't introduce further instability. And then cyber is increasingly essential to the grid. The smarter the grid, the more the cyber controls. There are operations in power grids that have to take place on very rapid timescales, and these are autonomous. There are others that can be planned on a scale of minutes, hours, even days, and of course then you also have the long-term planning that you anticipate a particular capacity in an area based on population and economic projections, and therefore you start building generation capacity now for something years ahead of time. Now, one thing is that a lot of life-critical structures, such as hospitals, may have backup generation, and they're able to go for a while in the case of a power outage. In fact, many facilities like this are required to have backup power, but they may not be able to fill all their needs. So one thing that may happen is they turn away non-critical patients, and they may decide that we have a limited amount of energy, and so we're just going to keep the ICU going, and the rest of it we're just going to provide service as needed. Also, increasingly, there are people who have medical devices in their home that they depend on for that they are at risk for losing their life if they lose power. What kind of backup power do they have for these? Probably these people would have to get to a facility that has power. Other infrastructures that are equally important, financial, and again, that means banks where you have a transaction that takes long enough that you're talking to a human, or ATMs. In addition to filling up their cars in anticipation of a disaster, people frequently get their cash. So you can imagine what happens if you have a power outage. We've all been through a power outage. It goes out, maybe a couple of minutes. It's annoying. In hours you begin to worry, and then, I better go to the ATM and fill up my car. But they depend on power, and you can't do that. So one population impact that maybe we as engineers don't often think about is you can have anxiety becoming panic in one of these situations. So what are some of the damages to independent infrastructure? There are several outage causes that don't really damage the grid all that much. You can have a cascading failure that can be due to what's called system protection. The system detects a fault somewhere, and there are automated mechanisms to trip off that part of the entire system. This is conceptually not unlike the circuit breaker in your house. You put too many things into a circuit, the circuit breaker blows. But there's no real damage, and you just unplug the hairdryer or whatever, trip the breaker back, and you're good to go. However, if it's sufficiently widespread, then we have the black start issue that I described previously. However, damage to the grid can also come from catastrophes, and this can be major storms, or in the region, I will talk more about the earthquake hazards and the volcano hazards. But this can significantly damage the grid equipment. I keep coming back, this is the look ahead, to the transmission system transformers, and I'll have a couple of pictures of those. But then an event like this can affect other infrastructures. So transportation, if you have an earthquake, road damage, bridges go out. So how do you get the crews out to bring the grid back up? It may be impossible to transport by conventional roads some of the large transformers. Now, speaking of mitigation measures, you do hear about occasionally if a storm is forecast. You can forecast certain of these natural hazards. Utilities will actually, they have places where they deploy crews ahead of time. And they're there, and they can be cut off from the home, from the main utility headquarters, but they've got freeze-dried food or whatever. They can go for a few days and fix up that part of this. This is usually what's called a distribution system, the lower voltage system that serves residential and commercial customers. But they're able to get out there and do repairs, being cut off from the system for a couple of days. And this is planned ahead of time. So you would think of that as a mitigation measure. Excuse me a second. This is a diagram of the transmission system in Washington, Oregon, and Idaho. And the Pacific Coast is on the left of the picture, and you can see that corridor, which is Interstate 5, which is the major north-south highway that goes from the Canadian border to Mexico. And Interstate 5 is also the urban corridor. You have the cities of Eugene, Portland, Seattle, Tacoma, Everett, and the associated suburbs. There are several big mountain ranges. Immediately to the east of the Interstate 5 corridor, you have the Cascade Mountains, many of which are actually considered active volcanoes. And then going further west, you have a series of mountain ranges actually going all the way to the Rockies. So everything that you're looking at there, really down to the coast. I don't know if you've ever been to Seattle, but it is, mountains come right up to the ocean pretty much. So it's very mountainous, and that constrains a lot of what you can do with the grid, because you have to construct transmission lines over natural mountain passes. So this introduces a relatively small number of single points or small number of points of failure where you could lose the transmission grid. For example, if you have generation into Idaho, you could, not too many, losing just a few lines, you would lose Idaho for some time. I should point out, by the way, that this area gets most of its power from hydro and is the Columbia River system, a number of dams. The area is a net power exporter. There's a high voltage DC line that runs from Oregon, well, actually near the Washington-Oregon border to Southern California. And high voltage directed current interconnect, HVDC. I hope I don't catch myself on acronyms too much. But these are systems that let you transmit large amounts of power over long distances without requiring the systems to be synchronized. You've probably heard the AC and DC. AC is alternating current. The current is pulsing 60 times a second in the US. Direct current is not. The way that the grid stays stable is that all the nodes on the system, the generators and everything, are more or less on that 60 cycle per second pulse. And if something is significantly off, then you have damage, you have outage, and it's bad. One advantage of high voltage DC is that you do not require the two systems that are connected to be synchronized. Geologic hazards are the big one, the big concern in Region 10, and these probably have the potential to cause a geographically extensive and long duration outage. Now, when Randy said we're concerned, when he introduced the talk, we are concerned about an extensive outage. You can have a distribution system outage. We've all experienced them. You can even think of having a blackout in Seattle for a few hours. That's not what we're talking about. We're talking about large, widespread, which would probably be a transmission system scale outage. There are two major subduction zones in the area. I'm not a geologist, but I lived on the San Andreas Fault, I used to ride my bike on the San Andreas Fault for many years, so I lived a few miles away from it. And that's a side slip fault, which is capable of earthquakes in the 6 to 8 magnitude range. The most powerful ones are the subduction zone quakes, which are potential for 9+. And the earthquake in Japan that caused the problem with the Fukushima plant was a subduction zone quake. By the way, I should point out there is one nuclear plant in Region 10, and it is not anywhere near the tsunami area, so that's not considered a concern. 10 of the 18 volcanoes classified by the Geological Survey as very high threat potential are in the Cascades, and then there are 5 more in Alaska. And by the way, they are near cities. So Mount Hood is very near Portland. Mount Rainier is, if you live in Seattle, Mount Rainier is beautiful. It's this symmetric, snow-covered cone, and there's nothing like sipping an espresso on the Seattle waterfront and looking at Mount Rainier and saying, I hope it's not today. So this is the subduction zone. As you can see, it parallels the entire coast, and unlike a side slip, as I understand it, one plate would subduct, it would slide under the other, and it would be over a wider area when it goes than the San Andreas. Personal experience with the San Andreas, it tends to go in chunks of 30 miles at a time or so. And as was pointed out in the introduction, this is a major industrial, technical corridor. We have the headquarters of Boeing, Amazon, Microsoft. Intel has probably their second largest presence after Silicon Valley would be in the Portland suburbs. So you have economic importance, high technology leadership, and what we call the defense industrial base. So this would be a bad thing to lose. And remember that most of that on the ocean side of the Interstate 5 corridor is in the severe shaking zone, that this could suffer serious damage. Anyway, so you can have, once again, the high voltage transformers are, think of these as the size of buildings. And they could be destroyed in severe shaking. One other issue that might not immediately occur to you is that the life-critical supply chain for Alaska depends on the ports of Portland and several ports in the Seattle area. So if you have a major earthquake that severely damages the port facilities, either in Alaska or here in Washington, Oregon, you could be relatively quickly facing a life-threatening situation to a large number of people in Alaska. This is a map of the Aleutian subduction zone, which is in Alaska. There was an earthquake there, I believe January a year ago, so about 15 months ago. I think there was not massive loss of life. There was a tsunami warning, but there was no significant tsunami. These were all very much dependent on the event. And it's noted that Alaska depends on ports and supply chain largely from Washington and Oregon. In fact, even if they're getting supplies from elsewhere in the country, chances are the last hop is through one of the Washington or Oregon ports. Just some of the volcanoes, as mentioned. Not only are there a lot of active volcanoes in the area, but essentially major cities are at or near the base of active volcanoes. And what are the hazards of volcanoes? I don't know how many recall a few years back, I believe it was 2010, there was a volcanic eruption in Iceland. And it grounded transatlantic traffic for some weeks. What happens is that this fine ash goes quite high in the air where planes fly, and as I understand it, think of it as ground glass. So it gets into the jet engine and does severe damage, also damages prop planes. As far as electrical substation equipment, ash can can cause arc flashes in substation equipment. And lahar is like a high-speed flowing hot mud, and you'll also hear, I mean, it's kind of literally fire and ice because many of these volcanoes are snow-covered year-round except when they erupt. And so you have the very rapid snow melt as this hot material comes out, and you have a mix of rock, snow, suddenly a lot of water, and it's coming down very fast. A lot of the plants and a lot of the transmission lines are taking advantage of the natural passes that, through which they can go, which tend to be more or less low points that get over a saddle in a mountain range. So you'll get these flows into the power station. And again, think of it as ground glass. It gets in the equipment, and it can do severe and lasting damage. Geomagnetic disturbances. We had several subject matter experts participate in this project. In addition to people who were experts on power systems, we had economists and people who were knowledgeable of population impacts. But one of the power grid experts who used to be at the University of Illinois, now he's at Texas A&M, that's Professor Tom Overby, is an expert on geomagnetic disturbances. So these are caused by certain solar phenomena, and they can induce a geomagnetic current, essentially, in long power lines. And it's not always, we have maybe a few days, 2-3 days, when one of these events is detected on the sun. We may have some hours before we know what part of the Earth will be most affected. And so what you could do maybe is you could decide to de-energize that part of the transmission system, take some people out, let the event pass, maybe a few hours, and then re-energize, and you have no damage. So that's one thought. There are devices that are being developed to deal with these. Now, one thing is that we have been maybe kind of lucky, but we haven't had a real major one in some time. There's one in 1989 that caused an outage in Quebec. And by the way, this is a northern latitude, or I'm sorry, this is a phenomenon of latitudes away from the equator, but Region 10 is, of course, all far north enough where they're at risk for the geomagnetic disturbance. So anyway, so this is the solar event I'm talking about is a solar corona mass ejection, and of course everything has a TLA, a 3-letter acronym, which causes changes in the Earth's magnetic fields. It also causes the northern lights, so beauty and destruction. But if you get a non-uniform electric field at the surface, and it all depends on a lot of properties of the ground, and I don't claim to understand it, but you can read up on it. What you need to take away is that you get one of these events and you can have destructive impacts on the transmission system in particular, and you can see the kind of scale. It can be quite, maybe subcontinent in scale, or it can be quite large. There were a couple of major events before the grid was fully built out. There was one in 1859 that we did not have an electric grid, but we had a telegraph system. And telegraph operators reported that the telegraphs were working clack, 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 spontaneously from the geomagnetic event. Now, going to human-caused hazards, yeah, you can have physical sabotage. When I started in the cyber resiliency or cybersecurity of energy systems, I talked to utility people, and somebody said, well, we're worried about somebody going in there with a screwdriver or a gun. And in fact, we have had in San Jose, California, there was an event of some concern. Somebody fired automatic weapons at some transformers in a major substation near San Jose, California. Now, this was kind of a blended attack. It was reported that they cut some fiber optic cables. So the fiber optic cables were the means by which the data came back for the system. So effectively what they did was they blinded the operator, and a lot of the cyber security language borrows from the military. They removed situational awareness. The operator lost situational awareness. And it was reported that whoever was shooting kind of knew which, either they were very lucky or they kind of knew which transformers were the most critical. So this was an event that was of high concern. There have been a number of cyber attacks against energy systems. People talk about the attacks against the Iranian centrifuges. That's a few years back. More recent, we have attacks against the Ukraine power system, and there were two. One of them was in 2015, 2006, and then the other one was the year later. They were almost exactly a year apart, and both of them were right before Christmas. So they were thinking that maybe a lot of people would have taken a couple of days off early for the holidays, and it would affect their ability to respond. Now, in the 2016 attack was of particular concern because they used means that, not unlike the way that attackers put malware on conventional enterprise systems, and the phishing spelled with a PH kind of attacks, then they were able to get through to the substation computer, which was not properly firewalled. And then at that point, they owned the HMI as the human machine interface. This is the console where the operator is visualizing the system and is seeing, the various measurements, voltages and currents, and maybe if there's a fault, then the operator is able to locate that, and something trips off, but then the operator can take corrective action after that. Now, one concern is that with these cyber systems that we have now in substations, is they depend on a number of protocols that are being developed. A protocol, think of it as the syntax and rules whereby either you talk to a machine or machines talk to machines. So for example, you have the web uses HTTP protocol, Hypertext Transfer Protocol. That's a protocol. There are protocols used in energy systems, and the real worry of the 2016 attack was that the adversary was controlling the system using perfectly correct protocol commands that were doing bad things. Another human hazard that we're concerned about, and this same colleague from Texas A&M, he's still a colleague, he's just not here anymore, is electromagnetic pulse, and he calls it GMD on steroids. So the EMP, the way it's generated is a high altitude nuclear detonation, and it generates a pulse that disables a lot of electrical equipment. And so there was, back when they were doing open air testing in the 1960s, there were grid impacts on Honolulu. I believe that's about 900 miles, 1,400 kilometers away. Hello? Okay. Okay, as I said, it can be triggered by a high altitude detonation of a nuclear device. And I believe that there's some concern about developing EMP generators that do not depend on a nuclear explosion. And as I said, GMD on steroids. One thing that we're not doing by treaty, we don't do atmospheric testing anymore, but we have a lot of microelectronics in everything today. So it's not merely a question of what it does to the grid, it's what it does to everything else, to your laptop, to your phone, to your car ignition, many significant impact. And this is some of the details of the starfish prime. HEMP, the H stands for high altitude. We're not for something else. And people who developed these systems theorized that they would be true from the beginning, and then they were observed in the atmospheric test in the 1960s. And you can see that the electromagnetic pulses drove the instruments off the scale, and a lot of street lights were knocked out, alarms were sent off, microwave communication link, and some satellite damage. So it's quite serious concern. Shifting gears, population impacts. There are risks to vulnerable populations, and Region 10. In addition, you have the urban areas, Portland, Oregon, Seattle, and so forth. But then you have tribal areas, and one interesting question that came up is that, well, people in the tribal and rural areas, they lose power all the time. They're more resilient. People in Seattle can't get to Starbucks in a half hour, they panic. So I don't know if that's true. This was said by somebody from Seattle, by the way. I'm not. You have disruptions in supply of food and water. So another thing people do in anticipation of a disaster, we all have water in our basement, right? In California, everyone would replenish their earthquake kit after an earthquake and then forget about it until the next one. I'm sure we're supposed to do it here for tornadoes too, but I'm not aware of too many people who do. So you have water, fill your bathtub, et cetera. But that only gets you through to some time. Water plants also have backup generation. And they're another one of these facilities that are often required by law to have on-site backup generation. And so you're able to keep that going until you run out of diesel fuel, unless these systems are not tested too often, and diesel fuel has a bad habit of developing gums in not too long. So I say, well, we have a diesel generator and we have a 72 hours worth of fuel, but it starts smoking and malfunctioning and coughing after 8 hours. So you really have to maintain your backup systems in the hope that you never use them, but you do have to keep up with it. And of course, you have with transportation, you have the whole farm-to-table pipeline would get disrupted in addition to not having the power. Now, I spoke previously about anxiety, and anxiety can lead to panic. And the longer things go, could you have a breakdown in social order? There's a concern of that. And in addition, there are long-term economic effects. And we had a subject matter expert who his field is business interruption, and studied what are the economic effects if you start losing people, and particularly losing the tech. Microsoft and Amazon decide to move their headquarters somewhere else. You could lose a significant part of your economic base. And he did a study post 9/11, and in fact this was observed. Business got on its feet pretty soon, but a lot of the affected major businesses moved out of the immediate area, even if they just moved across the river to New Jersey. But there's still some loss of your long-term economic capacity. Finally, high voltage transformers. So you need them for transmission system operation, and if you have a failure of more than a few of them, means you could lose the grid for months and possibly over a wide area. They're not made in the US, or none of them are made entirely in the US, and they're kind of one of a kind, so you really have to order them a long time ahead of time. And they're large and heavy, so they're difficult to transport in the best of circumstances. So you can imagine if you've had an earthquake and your roads are all broken up, you're going to have to get the roads in good shape before you can move one of these pieces of equipment. And again, just like the transmission system, the road system crossing the mountains north-south Interstate 5, not bad, but if you go east from there, you have to cross mountains, and geology just constrains where you go. And so you have, again, a relatively small number of points of failure. So what can damage to the high voltage transformers? Everything we talked about. Severe earthquakes, volcanic ash, sabotage. Now you can say it's difficult to destroy a large number at the same time unless you get several teams of evildoers to do physical damage at the same time. Unless you find a cyber mode that can do it. I'm not aware of one. There have been demonstrations of damage to substation equipment, but to my knowledge, not to a transformer through cyber means. And then, as mentioned, severe space weather and also electromagnetic pulse. So what measures can you take? Well, you can't afford to do everything, so you do a risk-based analysis of the threats. I think it was a generally agreed observation that you have a number of near single points of failure, not just dictated by the geology, but you also have, by doing careful analysis of the grid, you may be able to identify if we lose this bus or if we lose this transformer, then we lose this entire region. So let's harden that point. In fact, utilities do this. They call it contingency analysis. They are required by law to do N-1 contingency analysis. What happens? What measures do I have to take so I can lose any one component of my system and still keep going? I'll talk a little bit about recovery transformers and provisioning of spares and backups. I mentioned previously that sometimes utilities send out crews in anticipation of a storm, some kind of a predictable event. They also take out large spare parts and pieces of equipment that might otherwise be difficult to move, so they're ready to go. In case of cyber, you can think of a SCADA golden image, something you know is correct. And so you say, okay, well, we take system backups. Well, if your adversary's been in your system for a while, then you're backing up the adversary. So a golden image is a lot harder to do in practice to prove that you're correct than you might think. Another thing you've probably noticed whenever we've had recent hurricanes and so forth, that the utilities, people from Illinois, from Ameren will go down to Florida, and that's great. This is called a mutual assistance agreement, and utilities have them. And there are evolving cyber mutual assistance agreements. Now, no offense to the guys in the hard hat and the trucks, but they're not cyber guys. So these mutual assistance agreements would have to take cybersecurity professionals who are also aware of energy systems, the kind of people we're educating here. And then near and dear to my heart, what are new grid operational models? Can you break up into islands by design? Can you have microgrids to rebuild the system? There are pilot programs in this region where a community center is a microgrid. So you have, by the way, this region is also subject to harsh winters. Not quite as bad as here, but so if you have a power outage in winter and after a few, not too long, it can be a life-threatening situation. You tell people, well, we got this microgrid at the community center. Come on down, we got warm soup, and we can keep everybody going for a while. Finally, recovery transformers coming up. These are some pictures of transmission system transformers. These are from Region 10, and the one on the left is a 460 kilovolt, and then on the right is some kind of a base isolation, which is basically a shock absorber, and it can withstand, claims to be able to withstand a significant amount of shaking and not fall over and not break up. So these are some of the things that are done in earthquake country. Another interesting program, this is a DHS program. It's called REC-X. And this is from DHS Science and Technology, and it was a research demonstration. There's a picture of it there, and you can see kind of the scale it is relative to vehicles you might be familiar with. This is 345 kilovolts, so in capacity it's a little smaller than the one on the previous picture. But the idea was to make something that could be transported. I put portable in quotes because they were able to demonstrate under good conditions that they could get it from St. Louis to Houston. This was not at any particular hurricane time. This was just can we get it there, set it up, and energize it, and get it going? It took 6 days from Houston to St. Louis. How far is that normally? A day, day and a half? I don't know, but obviously they're not going 70 miles an hour. One interesting thing is if you look at the middle of it, the whole gray thing is the transformer, and the bottom of it is the base. So they get that whole thing out to the site. One thing when you have something this large and heavy is you just can't put it on the ground. So it's more or less self-basing. And by the way, one of the concerns in Alaska is with climate change that there's melting permafrost. So if you've got big, heavy equipment and the permafrost starts to melt, then you could have problems of it not being level, and that introduces difficulties. Microgrids is an area of research here. We're looking at a system of 2 microgrids. If you understand these diagrams, red means it's energized, which means that think of it as a closed breaker, and green means it's open. And this is a microgrid case where we have a critical load, and for some reason ESS is an energy storage system. Think of a big battery. And if we lose that, there's a power sharing agreement, and we signal the other microgrid, and we close that one green square on the bottom, and we can keep the grid going. So this is one of the projects we're working on here. A microgrid is a system connected to the distribution system. This is the low voltage side. And typically they're able to operate connected to the grid or in island mode. They can break off from the grid. And maybe they're more resilient. They have stability problems. I was the microgrid champion on the project team, and somebody said that we are a long way from microgrid energy being cost competitive with grid energy, and that's true. But then, I'm talking about that community center. The upside of it is you can keep people alive in a life-threatening emergency. And then also a restoration strategy. And in terms of Black Start, bring things up as ever-growing microgrids and larger islands and so forth. It's been observed in recent, particularly hurricane events, both in Katrina and more recently in Sandy, that sometimes the system breaks up and you lose significant parts of the system, but islands just kind of form because by luck, they balance generation and demand, and they're able to keep going for some time. And so, then instead of Black Start, it's a question of synchronizing and reconnecting these islands. So anyway, just touched on a number of the things we considered. There are a lot of natural and human-caused hazards that can cause the outage that we're concerned about. The geologic hazards are particularly severe, probably more severe in Region 10 than in any other FEMA region. Recovery and restoration face challenges because you can't just say, okay, the electrical system went out, this is how we bring it back. Oh no, but the bridge is out, we can't get a truck out there. So you have to consider the infrastructure interdependence. Probably what would hamper the long-term recovery the most would be if you lose a number of the high voltage transformers. And how you should mitigate this, consider a threat analysis, identify critical components, harden those, and by harden means you either have, you cyber harden them if that's what you're worried about, or you have a redundant transformer on site, or you have storage, for example. There's a lot of research in large storage systems, grid-scale storage systems. And then technology advances and new operational models such as islands and microgrids. I believe that's it. Okay. Back to you, Andrea. All right. Once again, if you're in the room, if you ask a question, be sure to push the button. Okay. In the back.
Can you give some examples of changes that were made because of this report?
Actually, the report hasn't been released yet, so we're in the final stages. It's in draft and it's being reviewed at FEMA. I did have approval to present this talk. Chances are that there will be a public version, but then there's nothing particularly sensitive here. But understandably, DHS and the Department of Energy are worried about giving too many details. This is where the critical transformer is, and if we lose that one, we're toast. So obviously you don't want to say that. No, so the stakeholders involved, we had a number of researchers. We had, again, it's a very multidisciplinary team, and we also had utility people. We had people involved in, from the state and local, and I don't know if we had any tribal in the room when we were having the stakeholder meeting, but we did have state and local, and federal, state, and local. So it's a diverse stakeholder community, and they get, kind of tailored versions of the report. But I think the goal is to make, make it mostly public. Public awareness would be a major benefit of something like this. That take it seriously. If there's an earthquake, right away get to where you can get power. Check in on your grandmother who's dependent on some home medical device or something like that. Anybody else? Andrea.
Okay, Al, there are some questions online.
Okay.
The first one is curious to know what type of costs would be associated with installing transformer base isolation. Ballpark increase in costs for installing that type of equipment on a new transformer.
I don't really know. It's my understanding that in this region, they install a transformer with base isolation anyway, so that's part of the cost.
Part two to that question. Relatedly, is it possible to retrofit a transformer with that kind of equipment, or is it limited to new transformers?
Again, sorry to say, I don't know. For some time, the transformers in this region have had the base isolation equipment, so we can think of that as the default condition. I'm sorry I don't have more information.
Here's another question. How would an EMP event impact backup generators? Would they also be disabled and need to be replaced?
So my guess is that the equipment would not have to be energized because it's a question of the current pulsing through the equipment in some way, but I'm not positive on that, but I would guess they would be damaged as well. There are, by the way, people are thinking of buildings that would be EMP resistant, but obviously there are limits as to what you can put in there. Building such a structure around a large transformer, again, it's a challenge. Anything else in the room? Okay.
Thank you, Al.
Thank you.